Okay, so if I ask you what's the data for the third person, how many siblings does the third person you asked have? You go, well, 1, 2, 3. Oh, the third person has no siblings. Okay, so this right here, we call that little index right there. It tells me where I am in the list. Okay. So the reason why this is important in statistics is they'll refer to the data as a to the n. A to the n refers to the nth person in the list. Now, this is also considered the general term. You can go ahead and copy that. And let me show you how this relates in math. Okay, now the difference between a statistics class and a math class is that a statistics class is going to get their sequence usually by polling someone. Okay, what a math class will do is usually we're looking at a sequence to try to look at a pattern. So let me do this. So in a math class, we're not polling people. We'll look at some list and go 1, 4, 9, 13, 17. And we'll just see some pattern, and then someone will go, what's going on here? Right? And when I look at that, I go, oh, I'm sorry, that's not right. Let me do that again. It's a bad pattern. 5, 9, 13, 17, 21. And then you ask yourself, what's the pattern? Now, if any of you have ever taken a IQ test, this is what an IQ test is. It doesn't really measure like your potential. All it does is it just measures, can you see a pattern or not? Some people are better at than others. It doesn't really mean that you're smarter than anyone else. It just means that for this one particular skill, I can see something and I could just see a pattern. Okay? It's just like having a good memory. It's just like, but this tends to be what an IQ test is built upon, right? So just so you know, if you ever take an IQ test and you don't score very high, you can actually practice it. And the more you practice finding a pattern, the higher you score. It didn't mean that your IQ potential was changed at all. It just means that at this one particular skill, you're a little bit better than other people. Okay. Now, we're going to first start with the generating term, and then we'll kind of look at this problem. Okay. If you're wondering what's happening at this problem, I start from 1, and then I add 4 each time. Right? I'm starting from 1. 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. But, you know, the pattern can be based on anything, division, multiplication, any kind of like weird thing. Okay. So let's look at what could be on your test, because I'm going to give you one of these types of questions on your test. All right. One of the following. So I'll say, given a to the n, find a to the n, sorry. Find a to the 5. So the only thing you have to do is make this connection that n is equal to 5. That's all you have to do is make that connection, right? Just pattern match. Oh, n is equal to 5. So then this should be equal to, and done. That's it. So this is a lot like saying, this is similar to f of x is equal to 2x plus 1. Find f of 5. So this is almost identical to function notation. Okay, so let me copy that, let you copy that, and then I'll tell you sort of the difference between sequences and function notation. Okay, now, whenever we have a sequence, n is a natural number, meaning that n is equal to 1, 2, 3, dot, dot, dot. It can't be a fraction, it can't be a negative number, it can't be a decimal, it can't be irrational, it can't be complex. N is a natural number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is nice, right? Because we like natural numbers. They're easier to deal with. Okay. In this case, down here, so for over here, n is a natural number. Down here, x is any number or expression. Right? I mean, we're allowed to have f of square root of 3. We're allowed to have f of 2 plus 4i. We're allowed to have f is equal to x squared minus 3x plus 7, and then we plug that into here. Like we've had a section that made us do this. Not quite this and this, but just so that f, whatever you plug into f, it can be anything that we've done, an expression, any kind of number that there, a fraction, a decimal. So this is a lot more flexible. And this over here, we have to adhere to the list nature of a sequence. In my list, I don't have the half person that I'm pulling. I can only pull person 1, person 2, person 3, person 4. There's no -1 person or 1.3 person or 4 5/5 person. Each person has a specific position in the list, and it works like the same person, right? First person, second person, third person. Okay, so let's take a picture. Okay. So if I want to make this this particular problem a little bit harder, there's kind of two things I can do. So let's look at those two things. One of them, I could give you something like this. A to the n is equal to this actually, let's make it n squared just for fun. Let's make it 50. Okay, so let's look at this. This will be minus 1 to the 50 squared. Okay. Now let's look at this thing right here. That's the thing that's a little bit weird. So I know that minus 1 to the 1 is equal to minus 1. Now I know that minus 1 squared is equal to 1. And then minus 1 cubed is equal to negative 1. And minus 1 to the 4 is equal to 1. And we could sort of look at that pattern, and it would turn out that if this number is even, you'll get number 1. And if this thing is odd, in terms of the exponent, you'll get negative 1. Okay. So this right here is even. And this will be equal to 1 times 50 times 50 is equal to 2500. All right. So that's one thing you have to keep in mind, right? That if the exponent is even, you get 1, and if it's odd, you get negative 1. Okay, so that's one thing, right? And I want you to notice that this goes from negative, positive, negative, positive, negative, positive. I'm sorry. Negative, positive, negative, positive. Okay, the sign flips every time we count through each one of these. Okay, so that's going to be important, not now, but that'll be important down the line. Okay. Now the other one is something that looks like this. Let's say 3. So go ahead, copy that. Thank you very much. So this right here, in math, we call that factorial. If you are using a computer, to say the word exclamation point takes forever. Just like you don't hear me say parenthesis. You hear me say paren, right? So usually in computers, we always shorten everything because we're lazy, even when we talk. So if this is a computer, the way you mention the exclamation point, you would call it a bang. Okay. So this is equal to 3 factorial. And then every so often you'll hear me call it a bang just because I'm more a computer person than I'm a math person. And every time I look at that, I have to like double check it. Is that that's a factorial? Because for me, when I look at that, that looks like 3 bang. Okay, now, for those of you using going to statistics, this is going to be used all the time. All the time. Any of you who go into probability, statistics, this will be used constantly. This is equal to 3 times 2 times 1. You count from this number and go down. This number here has to be a natural number, meaning that it can't be negative, it can't be a decimal, it can't be a fraction. is going to be positive and a whole number. Okay. So you just start from the number, you walk yourself down. 3 times 2 times 1 is 6. So go ahead. Why don't you find 5? Why don't you find A5? Okay. So this becomes 5 factorial. It's equal to 5 times 4 times 3 times 2 times 1, which is equal to 12 times 10 is 120. And then just for your own notes, I don't think this is in XYZ. Just know that if you have 0, this is equal to 1. Okay, so go and copy that, and then I'll explain to you what the factorial is used for. Okay, now let's talk about where that comes from. It's not going to be used in this class. In this class, we'll just give it to you physically like this. Okay, but let's talk about where would you use that in math? Okay, so let's talk about that. So for me, I've got a brother and a sister. Okay, so if you were to ask me how many ways can you order John, Dean, and Ann? So if my mother called us when we were little kids and said, line up, how many different ways could we have lined up, right? Well, I could have come first. Dean and then Ann. Or I could have come first, and then you could have had Ann and then Dean. You don't have to write this down. It's not on the test. I just want you to see where this comes from. Why this would show up in statistics a lot. Okay. And then you would say, let's say my brother beat me. He's older than me. And then I would have John and then Ann. and Anne, and then John. But let's say my sister, she's the smallest, so we just let her go ahead of us. And there would be 1, 2, 3, 4, 5, 6. Now, the way you would calculate that, you should go, how many ways can I order 3 people? Well, let's say 3 factorial. If there were 4 people, it'd be 4 factorials. 5 people, that'd be 5 factorial. And then you go, well, how did you figure that out? Well, let's see. How many different ways can I pick the first person? 3. I can either pick John, Dean, or Anne, right? So there's 3 ways I can pick the first person. Once I pick myself, once I know that I got in front, how many ways can I pick who comes in second? 2, my brother or my sister, because I'm out of the list. I'm already first. Once we pick 2 people, how can I pick the third person? Just 1 way. And that's why you get 3 times 2 times 1. So anytime they look at a lot of times in statistics, you'll say, well, there's for the Democratic presidential primary, we had about 20 people. And you're like, well, when people vote, how many different ways can people vote? Well, 20 bang. Meaning that that's how many different ways Joe Biden can get the most, or Elizabeth Warren can get the most, and then Sanders get the second, and then Klobuchar gets the third. Like that is the number of different ways in which these orderings can happen. So that kind of question is asked a lot in statistics. Okay, so let's erase this board. None of this is on your test. Okay, now the other way I can, yeah, go ahead.
Wait, so factorials in general won't be on the test?
No, just computing a factorial.
Oh, okay.
Okay, but in terms of like, I'm not going to ask you, there are 5 people in a race. How many different orders can people finish the race? Like that's a typical way you would ask this question. But I'm not going to ask you any kind of statistics question. Usually in an intermediate algebra class, that very last day, some classes will have it, some classes don't, but it's usually not heavily looked at until statistics. In our school, we decide we just run out of time, we're not going to cover it. Okay. We're just going to leave it for you in statistics. Okay, so let's do the second part. Okay. Write the first 3 terms of a to the n is equal to 2 times n bang. Okay. So when they write this, we want to know what A1 is equal to, what A2 is equal to, and what A3 is equal to. You have to bring to the table that your list starts at A1, always 1. If you're in a computer class or an engineering class, it starts at 0. Because unfortunately, computers and mathematicians can never get on the same page of what number a list starts from. And unfortunately, all of our formulas are off by 1. So this is a math class, so it's going to start by 1. And for those of you who are computer majors, you'll jump into your computer class, and then they'll go, it starts by 0. We ain't mathematicians. We're engineers. So unfortunately, for those of you going to be engineers or computer majors, you'll learn all of these formulas one way in math, and then you'll relearn them all in computers. Okay. But since it's a math class, go ahead, do that. Plug in, find A1, and then find A2, and then find A3. Okay. And then just know that when you have this multiplication, just know that factorial has precedence. So you do the factorial first, and then you do multiplication. So even though there's no parentheses there, it's there. I have that there. Oh, I'm sorry. This is a 2. Do that last one. Okay. This last little part, so what we've been doing is we've been going from the general term to the actual sequence, right? My sequence now is 2, 4, 12. And this next part is how do we go from the sequence to the general term? So that, let me give everyone a second to copy, and then I'll show you that original problem that I gave you. What's the pattern? Okay. So let's start with the original problem that we started this lecture with. The original problem was that we have 1, 4, 1, 5, 9, 13, 17. Okay. And what we said was, what's the pattern? Okay. Now, that doesn't sound very mathy. The way we would write that in a math class is we would say, find a n. Find the general term. What is the general term where when I plug in 1, I get that? When I plug in 2, I get this. When I plug in 3, I get this. Okay? So let's work our way toward that. Let's try this one. This is A1, this is A2, this is A3. The question is, how do I write something where when I plug in 1, I get a half? Where I plug in 2, I get 3. When I plug in 3, I get 4. Now, this is in your homework. I will not put it on your test, right? The main reason why is that I don't know how to teach it, to tell you the truth. Most of the time, I can like fractions, calculus, anything. I can like walk you up to it. I go, this is step 1. Here's step 2, step 3. Follow the steps. Boom, done. Let's go. Okay. Unfortunately, this is like an IQ test where it's just, does anything pop in your head? Does it not pop in your head? Well, I guess you don't get a degree then. I hate questions like this. So what will happen is that in this section, you'll be in your homework. I won't put it on the test. And then what will happen is that you'll get the same question in pre-calculus with about the same difficulty of questions. And it'll be the second time you see it. Because you did homework, I kind of see it now. You get a little better. And then we take Calc 3, they'll make these a lot harder. But in pre-calculus, they'll give you, like, if you see something that starts with 1 and you're adding 4 or you're multiplying, or you're like, they'll give you tools to like break it down. Usually what happens though is this first section, we give you no tools and we say, just guess so that you can appreciate the tools. So for me, I don't think that's a great thing for me to judge you by in terms of your grade. So it's on your homework. So you have exposure to it. Those of you who are going to take pre-calculus, sit down, look at it, see what the answer is and go, huh, okay. And then when you take pre-calculus, it'll be the second time you see it. Okay. For those of you who are only taking statistics or business calculus, you'll never see this again. Don't stress it. Okay. So what you want to do is you want to sort of say, how can I look at this? Well, what is the same for all of these? What's the same for all of these is I have a 1 dash. And then what I'm going to do over here is say, well, this is one bigger than this. This is one bigger than this. This is one bigger than this. So then I'll do n plus 1. So when n is equal to 1, I get 1 plus 1, I get 2. When n is equal to 2, I get 2 plus 1, I get 3. When n is equal to 3, I get 3 plus 1, I get 4. So go ahead and do this one, right? We're starting with 1, and then we're adding 4 each time. And just see if you can do it. the way I kind of see it is I see 1 plus 0 times 4. That's what this is, right? I start with 1 and I multiply by 4 every time. So for this one, I get 1 plus 1 times 4. That's what gives me 5. Then I see 1 plus 2 times 4. That's what gives me 9. Then I see 1 plus 3 times 4. That's what gives me 13. Right? So this is A1, A2, A3, A4. And then people go, well, how'd you get that? I'm like, just experience. You do this enough time, you start to see like, oh, there's these patterns that get repeated all the time. This is a start by 1, and then I'm adding 4 every time. So then this would turn into something like 1 plus n minus 1 times 4. Or you could do something like minus 3 plus n times 4. That would work also. Okay. So you could sort of see that there's no like, what's the first step? It's like one of those things where it just kind of pops into your head. And then if you want to know strategies to do this, take pre-calculus. They'll give you a few strategies. But for the most part, it just kind of pops into your head after you do it a bunch of times. Okay? So it's on your homework. You got like 4 or 5 questions. If you end up skipping it, will not harm you. Right? Think about how many questions you've done. Homework is only worth 10%. So if you skip it, it's not going to harm you at all. So for those of you taking pre-calculus, sit with it a little while. Those you don't, go ahead and skip it. Just start working on the final. Okay, let me take a picture of this. Okay. So go ahead and copy that. And then we got one really important thing to cover in this section. One more. It's not hard. It's pretty straightforward, but it's really important. Okay. So let's reach this. All right. So I'm going to give you one question where I'll give you the general term, and then you tell me what A1, A2, A3 is, or A10. Okay. Where you just plug in n into the general term, and that's one of the questions on your exam. Now, the other thing we're going to do is we're going to work on summation. So this is summation. Sometimes they'll call it sigma notation. Now, It's called sigma because that's the capital letter sigma in Greek. Then if you go, why are you guys using Greek letters? At a certain point, you just start running out of letters. People keep discovering things. There's only 26 letters. That's why in terms of real numbers, we use that for real. So at a certain point, you run out of letters. You're like, well, let's create different fonts, you know? So, you know, you start trying to like come up with new variables that represent something. So then you start trying to get different fonts. And sometimes you just go like, I don't know, let's pick a different language. And then you'll go like, okay, what language should we use? Really, we should use Arabic, right? So the letter X comes from the letter, I don't know I'm not Arabic, but there is an Arabic letter called chi, right? All the letters that we were using wasn't X and Y, those are Latin. When you read the original Arabic algebra books, I guess they'd be scrolls at that time because they didn't have books when they created this. There was no printing press. So they'd be like, you know, scrolls that are put together. The Arabic letters got transformed into Latin letters, and that's why I use X, Y, and Z when we graph. But for Arabic, it'd be chi. So it would make sense that we use Arabic, but then culturally, Arabic is not part of the Western civilization tree. So then we just started using, well, Greek letters, because even though our algebra came from Muslims, from Arabs, and mostly Arabs, some Hindu, but mostly Arabs. All of our geometry, which is what math started with, was more geometry, not algebra. That stuff all came from Greece. So we also use Greek letters just because we run out of regular letters. Okay, so this is sigma notation. Okay. And then let me use the same variable that your XYZ homework does. It uses I. Okay, so it uses I is equal to 2 to 4 I squared. Okay. Let me move this over here. Okay. So this right here is sigma notation. And this is used for partial sums. Let's just keep that on the side. Don't worry, there's a lot of scary words, but what we're actually going to do is not that bad. Okay. So this is our starting number. And this right here is our ending number. Okay. So we're going to start from this number, and then we're going to count to that number. We're going to go 2, 3, 4. Right? If you can count, you can do this. Right? We call I like a counter. What it does is it counts from this number to that number. Okay. Now note the term sigma and summation and sums. Sum means add. Right. So we're going to add each one of these. So what are we going to add? We're going to plug in I into here. So in this case, I is equal to 1. In this case, I is equal to 2. In this case, I is equal to 3. And then we're just going to sum those together. And then done. Okay. Now, let me try another one for you. So do that. You're going to count from 1 to 4, and then you're going to plug 1 in here, 2 in here, 3 in here, 4 in here, and then you're going to add them up. And for those of you who haven't taken the SAT, this is on the SAT.
Professor?
Yeah.
I was on my calculator and I have a key on my calculator that allows me just to plug in numbers to get just to plug it in right into summation form. And when I do it, I get 29. Not
for this one?
Yeah.
Oh, you know why? Shoot. I'm starting from 3. I'm starting from 2. My bad. Okay, 2, 3, 4. My bad. I'm sorry. Thank you. When you just start counting, you just forget that you're starting from 2. Okay, there you go. So the mistake I made is starting from 2 to 4, and I put in 1 there, which is what's messed me up. So we have I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, and then we're going to add each one of these. And we're going to add 2 times 1 minus 3, 2 times 2 minus 3, 2 times 3 minus 3, 2 times 4 minus 3. So then I get minus 1 plus 1 plus 3 plus, let's see, 8 minus 3 is 5. So you should get 8.
Professor?
Go ahead.
It could be because I'm inputting it wrong, but my calculator says 32.
32?
Yeah. So I don't know if I'm inputting it wrong in the calculator or...
It could be. Let me double check. No, I think I'm right on this one. Let's see. Minus 1, 1.
Yeah, because when I did it on paper, I got 8, but the calculator says 32.
Yeah, it could be how you're inputting on the calculator. And if you were to ask me, how do I do that on my calculator? I would go, I don't know. My teachers in high school and college never let me use a calculator. So you guys are probably much better with a calculator than me just because I've been shamed. Okay, now, but I can do it in Excel because my teacher said Excel is fine. Computers are good. but they told me calculators are bad. So when everyone was getting these nice TI calculators and statistical calculators, I look at the young teachers who are one generation younger than me, and they're great with calculators. And I, for the life of me, just cannot use a calculator because my teachers shame me that you're not allowed to. Okay. Now, there'll be one of these summation questions on your exam. Okay. Now, like the sequence problems. Oh, but even before I go there, okay, let's talk about why it's called the partial sum. Okay, it's called a partial sum because we're not going to infinity. There are some sums that we study that go to infinity. And then a lot of times when you think about that, like, why would you add an infinite number of numbers? I don't understand what that's good for. Okay, so the idea that this is a partial sum is that that number there is not infinity. Okay, if you were to look at just sums, like let's say that is what an infinite sum would be. An infinite sum goes on forever, right? And then when you look at that, you go, isn't that equal to infinity? If I add an infinite number of positive numbers, shouldn't that be infinity? Because it's an infinite number of positive numbers. And the answer is actually no. It could be infinity. It could be, or it could just be a number. Sometimes when you add an infinite number of positive numbers, you could actually just get a value like 16. And then the next question is, well, how the heck would that happen? Well, this isn't on the test, so you don't have to write it down. But if you think about it, here's one box. I want you to give me half of the box, and then a fourth of the box, and then the eighth of the box, and then the 16th of the box, and then the 132nd. And then the 164, and then the 128, and then the 256, and then the 1 over 1024, then 2048, and 4096. Okay. And if you go all the way to infinity, you will have coded in one box. Okay. So if you want to learn about infinite sums, Calc 3. So that's where this word partial sum comes from. It just says there's a finite number of these. Just add them up. Okay. Now, this was discovered by Zeno hundreds of years BC, before Christ. So this has been around for, not quite 3,000 years, but getting there. There's another infinite sum that's very famous. It's not on your test, but I know that the stat teachers like me to just talk about it. So let me just introduce it to you. It's not on the test, but it's awesome. Okay. This was discovered by a third grader. His name was Gauss. Friedrich Gauss is probably one of the greatest mathematicians ever. Now, in the summers, I used to teach. A bunch of 5th grade, 6th grade, 7th graders math for, geez, how many hours was that? It was from 8 to 1. So I would teach them math for 5 hours a day, and you'd have to find stuff to do because 5 hours a day of just of math, man, that just sucks. So what I used to do is I would give them this problem. I go, spend the next hour working on this, and they'd come back to me and they'd go, 4,932. I go, no. And then they'd go like, where's my mistake? I go, I don't know. Probably somewhere in the beginning. Start again. And then they would spend the hour like adding it, not getting it. Sometimes maybe someone would get it. They kick back, right? So Gauss had the same teacher where he just wanted to kill time, and he just said like, well, you guys add that up. Then Gauss came back and immediately told him the answer. The teacher asked him, how'd you do it? Because he's a third grader. And he said like this. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98, 101. Okay. And then you ask yourself, well, how many pairs of this 101 are there? Well, there is 50 plus 51. This one is 101. You go, how many of these pairs are there? Well, 1 to 50 is 50. So this is equal to 50 times 101, which is so they've come with people have since then developed a formula for this, going up to n minus 2, n minus 1, n. Okay, so they'll use this in stats. So when you add these together, you get n plus 1. And if you go, well, how many of these n plus 1s are there? Well, this will go all the way to n divided by 2, n divided by 2 plus 1. So there'll be n divided by 2 of these. So this is equal to n divided by 2 times n plus 1. So the succinct way of writing this is n equal 1 to, I is equal to 1 to n is, of I is equal to n over n plus 1 divided by 2. So that's not going to be on your test, but when you take your stats class, they'll talk about this. When they talk about your pre-calculus class, they'll talk about this. If you walk into a computer class and you have to study how fast does this algorithm or this procedure run, they'll talk about this. So this is just something that'll pop out. I just wanted you to see it because someone's going to show it to you again if you're going to be a science major. And just know that this was created by a third grader, one of the greatest third grade mathematicians ever, but still a third grader. When I was in high school, my high school teacher asked us, he goes, what's your favorite mathematician? And all of us were like, I don't know, are we supposed to have a favorite mathematician? And he goes, Friedrich Gauss is the greatest mathematician ever. And I remember we would joke around with each other going, who's your favorite mathematician? And we were, Friedrich Gauss. And then my friend is a epidemiology doctor in Seattle. So he's been working with the school districts and writing these papers, trying to give just regular layman direction on what we should do with COVID, what's the current status of the data. And he had just written this Facebook article that he had given to the school district, and then he just CC'd me on it. And in the middle of his thing, he's talking about Gaussian distributions, right? And I emailed him, who's your favorite mathematician? He goes, Gauss, yeah. All these years later, 17, when we're 17, our teacher is telling us Gauss is the greatest ever. And, he's 53, and like his paper is like, well, Gauss said this, Gauss said this, Gauss said this. Gauss really is the greatest mathematician ever. Okay.
Professor?
Yep.
But for the exam, only basic summation will be on there.
Very basic. That's it.
Okay.
Okay. But I just want you to be exposed to this.
Okay. Thank you.
Okay. Now, I want to expose you to one more thing. Why do I have to know this? Okay. Let me show you what your formulas are going to look like in statistics, because they're very different from your other class. And a lot of times when you walk in there, you're a little bit uncomfortable with the notations. The teachers are supposed to explain it to you, but a lot of times they don't sit you down and do so. So let me sort of explain it to you. Let's say I have these numbers. Okay. And I ask you to find the average. Right? And then you go like, and then your neighbor goes, how do you find the average? And then you try to hand wave it at them. You go, add the numbers and then divide by how many are there. And you know, that's probably how you were taught. That's how I was taught when I was a kid. Add all the numbers and how many are there. Now, once we get in statistics, the formulas start getting very involved, but you're not allowed to like do that. Like if you go into a meeting and you go like, this is how we calculated it, and you just use words like that, they're not going to pay you a lot of money. They're going to pay you a lot of money if your formulas look fancy. So the first thing we do is we don't use the word average. Why? Because people understand average. You use a scary word, mean. Mean and average are exactly the same thing. Okay. Now, what happens is you would write it like this. You don't even write n. This and this are the same thing. So what this is saying is add A1 and A2 and A3 all the way up to the last A. Over here we have 5. And then divide by 5. The assumption is that you start at 1. So a lot of times they won't write 1 here and they won't write n here. You just assume that n is going to be the last one in the list and the first one in the list is going to be 1. Okay. So this is how they'll write their problems. Now, there'll be things like standard deviation, which will be a little more involved. It'll be AI minus, let me just pick a number. And what they want you to do is subtract the first one, square it, subtract the second one from 5, square it, and then divide it by how many are there. So what happens here can be quite involved. All this means is do this to each individual number in the list, and then take that result and add them together. So this is something you're going to be doing for stats. This is the notation they're going to use. This is what I'm trying to sort of prepare you for, just something on this level. Okay, so that when someone uses notation, you can go like, subtract every 5, square it, add them all up, and then divide by how many are there. Okay, again, not on the test. I just want you to know what your notation will look like in the next class. Okay. Let's take a 10-minute, let's take a 14-minute break. We have a lot of time. We're doing good today. So let's finish at 9:25. When I come back at 9:25, I'll tell you what's on the test and then what our schedule is for this week. Okay. So, well, you're going to have a moment of writing frantically. So let's take a break, go to the bathroom, get some caffeine, and then I'll list what's on the test, and then you'll write frantically. Okay. Thanks, everyone.
Professor, are you there? I have a question.
Okay, so let's get back to it. Let me share screen with the haiku. All right. Nothing in algebra has changed over the last, I don't know, 600 years. So what I thought was important, last semester, since there's no new change, is still important this semester. So what I've done is I uploaded a few finals. So over here I have 2 finals, and then down here I have 3 more finals, right? So sometime today, what I'll do is I'll update the what to study from those finals. So if you want to get a sense of like what is on the test, my finals, about 80% of it is always the same. Ooh, where did that come from? Let's get rid of that. 80% of my finals are always the same. 20% switches depending on the semester. Now, sometimes we add things, sometimes we delete things. So there may be things here like this right here is something I don't have to cover. The 134 exam should be very similar to the 125 exam. The only difference is the word problems are different. So I'm going to write a what to study, because most of most of these finals, I just look for an example of those questions on XYZ, and I put them on your final. So your final, the final tally is 40 questions. It's 3 minutes a question. When I looked at how long everyone was spending on a question, in general, people are spending about 1.5 minutes. So, and the vast majority of the people are nowhere close to running out of time. Go ahead.
Can you show one more time where you put that on the haiku?
Sure. So let's share screen again. And let me go to the haiku. So right here are the practice finals. Right in the middle, here's 2. Okay. But there's 5 actually total. So if you go down to this one here, the 134s, they're also, oh, this one's not here. I'll put this one up here. Actually, I'll put it up right now. The 134 finals and the 125 finals are both valid. Now, some of them have questions that we didn't cover because every semester we argue with each other as to what should be on the test. So, I will go over sometime today on which questions you should ignore. Okay. Let me make sure.
Okay, thank you.
Yeah. And then let me make sure.
Professor?
Yeah, go ahead.
I was going to ask if I was doing the practice quiz for quiz 3, and I finished it, but I want to do it again, but I'm unable to do it again.
Okay, so I will fix that. For quiz 3, I'll fix that by. So people are still doing it tonight, so I'll try to make that available on Wednesday for you to re-practice quiz 3 over and over again. Okay. Actually, I can make the midterm available for you guys to practice today. I can make the quiz 3 practice available for you to practice. And then the actual quiz 3, if you need an extension, I need to know today, because if you're not getting an extension, I'm going to make it available for everyone to work off of. Okay?
You know, I was asking if we can have the practice available today because I want to retake the practice again before the quiz.
Yeah, I'll fix that also.
Okay.
So let me put that. Let me write it down and let me write that on my list of what I have to do today. So make quiz 3 and the midterm and the actual midterm available. Okay, and then I've said this a million times already that basically all the questions are taken from the practice quizzes and the actual quizzes and midterms. Okay, so I'm going to write the list of what I'd like to put on the exam. Okay. Now we said that from section 12.1. There's 2 questions, and they'll be pretty straightforward because you're learning them today. And then we're also going to cover an ellipse, and hyperbola, and then there will be 1 question each. Okay. Any question that says, oh, let me also, there's also 1 section that we didn't cover, and I'll email that video out for those of you who want to look at it. Now, almost all the questions that say solve are on the exam. So you have solves with square roots. You have solves with rational expressions. Again, I don't know if these work or not. I'm just writing them so you sort of know what they look like. You have stuff that looks like this. There's no completing the square, quadratic formula. Then you have ands, and you have ors, you have absolute value, you have in-betweens, you have inequalities. What other kind of solve problems did we have? Oh, you had factoring. So you had something like, oh, and then you had the inequalities. Rational inequalities and also quadratic inequalities. Let me give everyone a second to like breathe and contemplate. So the way I usually create my exam is I first go through every different kind of solve problem. Oh, and then 3 by 3. So that's the X, Y, and Z. That's always on the test. And then you have the formulas. You have the formulas like midpoint, distance, circle, find the radius and center. Midpoint, distance, circle, quadratic formula, slope. Okay. Oh, and vertex. Oh, and then over here, we have the logs. And then we always have exponents. So definitely exponent, definitely logs. Those are always there. And then there's domain. There's probably 2 or 3 questions that ask for domain. And then graphing. In terms of graphing, I don't ask exponents, I don't ask square roots, but I always do ask lines. And sometimes, parabolas come up a lot. And then we're going to learn ellipse and hyperbola today. And those will come up. Those will definitely be there. And then you have the extras. So there is long division, or you can use synthetic. There is inverse questions, composite, complex numbers. I'm trying to think, is there anything else that I usually have in there that I forgot? So then this is 90% of the exam. And then the other 10% is just random problems, simplified problems, foiling problems. Excuse me. Okay. So go ahead and copy that. So when you go through the old exams, I try to just pick the X, Y, Z problems that are similar to what I put on my old exams. So once you do like 2 or 3 exams, you'll have a really good sense of what I ask. I ask the same things over and over and over again. So by the time you take the exam, there really won't be any mystery. Okay, so let me give everyone a minute to copy because I know there's a lot there. And you copy slower when you're stressed out. So let's talk about this week. Oh, actually, go ahead. Let me give you, check something real quick. Go ahead, keep copying. Yeah, so I made sure the final is available from 11:30 to noon on Saturday. And then that Saturday is an immovable date. So if something happens between then and now and then, talk to me. Okay. Okay. Let's talk about this week. So we have Monday, Tuesday, Wednesday, Thursday, Friday. So Friday, there's no class. You just take the exam. Turn it in, you're done. So take it anytime on Friday, right? On Thursday, there's no lecture. I'll answer questions. So what I want you to do on Thursday is just start going through my old finals or going through the XYZ and doing the old exams and the old practice exams again. What I'm going to do is between 8 and 11:30, I'm just going to be here just having Zoom office hours. So the thing that I want you to do the most is sleep. So on that Thursday, sleep in. And I'm just going to be available at any time. I'll just be here watching The Office. And anytime you have a question, just yell out and I will, explain anything you want, do any question you want. The whole thing here is I want you to get real sleep so that Friday you're ready. Okay. Then on Tuesday and Thursday, I'm going to review. So I'm going to review starting from what's oldest. So I know that the ands and ors have probably left your head already. The absolute values have probably left your head already. So I'm going to start with the oldest stuff and the stuff that's easiest to do to pick up points. So stuff like 3x3 system of equations, I'm probably not going to cover that only because in the time we could do one problem, I could do a bunch of other problems. So at this point, in terms of our review, I'm just going to go through what are the things I usually put on the test and what are the things that you can get the most points quickest. And the things that are just sort of like long and cumbersome, I'm just going to skip, okay? And then you can ask me for those things on Thursday because, again, I'm having office hours. And then over here on Monday, this is the last day of new material. Okay. Does anyone have questions on our schedule for this week? And the final is available from you from the second this class is over, 11:30. It'll just pop up in there. Okay. So you take it when you're ready. Okay. So let's clear the decks and let's finish up our last two sections. Okay. And then we'll erase this. Okay, so let's go to section, what section are we on? Section 10.3. Okay, cool.
Professor?
Go ahead.
Did we cover how to go from like a list of numbers to summation notation?
It's the same thing as going from as doing sequences. So let's say we have something like this. of one, let's say 1/2, 1/3, 1/4, 1/5. Okay. Oh, we'll just stop here. So there's 4 of these. And it's just, can you see it? So in this case, this would be 1 over I plus 1. So you just count how many are there, 1 to 4, and then you just say like, okay, 1 plus 1 is 2, 2 plus 1 is 3. So it's just like those sequence questions where I said it's not going to be on the test. I just want you to be exposed. And a lot of it is, does it pop into your head or does it not pop into your head? Okay. So the only difference is you just put the summation in front of it.
Okay, thank you.
Yeah. Okay, now let's talk about ellipse and hyperbolas. Now, I am usually, when it comes to mathematics, a whiner. Why are we learning this? How am I going to make money out of this? This is stupid. Why am I learning this, right? And for some reason, I like conic sections, only because when I was a kid, I kind of looked at this and I go, why are we doing this? This is stupid. And then as I became a math teacher and I read about the history of math, conic sections is a 3,000-year journey in math, which is actually kind of beautiful. The story behind it is beautiful. So the fact that you're probably not going to use a lot of these things, even though they appear in nature a lot, the story of this is pretty cool. So we'll tell you the story at the end. Okay. Now, first, let's make sure that we are on the same page. Okay. This right here is an ellipse. It is not an oval. So if any of your kids are going to preschool or they're going to a well-supplemented, as Obama would say, a high-quality pre-K class, they'll tell the kid that it's an oval. And my daughter, she came home, she's 3, and we're doing her homework, and she's like, that's a square, that's a triangle, that's a circle. And then she goes, that's an oval. And I go, no, baby, that's an ellipse. And she goes, no, it's an oval, because I saw Dora and Dora told me it's an oval. Mrs. Hilda, my teacher, she's really smarter than you. She said it's an oval. And I said, baby, do you know how much education I have compared to Miss Hilda? Let me just tell you. Let's bring up a dictionary. Oval means egg-shaped. An egg is not symmetric. It has a big end and a small end. Egg-shaped. That's not egg-shaped. It's symmetric. It's an ellipse. See, the way you create an ellipse is you put 2 nails in the wall, and then you have a string, and then you have your pen, and you stretch the string out as far as it can go, and it creates an ellipse. And my daughter goes like, but that's not what Dora said. I go, baby, Dora's a moron. Dora walks out of her house. She gets lost every day in her backyard. She's an idiot. Don't listen to a moron, to Dora. Your dad's got a PhD, baby. Come on. I do this for a living. So the only thing that happened is made my daughter cry. She went to my mom, my wife. My wife looked at me like, Dora is a moron. Just so you know, right? She's like constantly getting robbed by the same stupid fox. Now, years later, my daughter's now 12. Last year, she's watching Dora and Friends. She goes, no, Dora, they got this new Dora show. She's in high school. And you know what? She's still getting lost in her backyard. Maybe she is stupid. So, just so you know, it comes around. My daughter agrees with me now. This is an ellipse. If you write oval on your final, I'm flunking, right? Ellipse. Now, let's talk about how to graph an ellipse. So let's look at the basic ellipse formula. It looks like this. X over a, x squared over a squared plus y squared over b squared is equal to 1. The way that you know that this is an ellipse is this is a plus. If it's a minus, it'll be a hyperbola. So I'm not sure how your homework is set up, whether it says graph or whether it says graph and ellipse. Just pay attention that if that's a plus, it's going to be an ellipse. Okay, now. The way we want to think of an ellipse is it looks like, it looks kind of like a cross. What happens is this distance right here is equal to A, and this distance right here is equal to B. Now, you don't have to, but I like to create a box around this, mostly because when we draw a hyperbola, we're going to draw a box. And I like to draw the hyperbola and ellipse in the same way because the formulas look almost identical, except that's a negative for a hyperbola. So I like to just do the setup the same, so when you do the hyperbola, there's nothing new. Okay. And then your ellipse hits these ends of these of the cross and fits in that box perfectly. Okay. So let's say we have something, and I say graph an ellipse. Let's say x squared over 9 plus y squared over, let's call it 25, is equal to 1. Let me give everyone a chance to copy. Yeah. So we know that this is equal to a squared, and we know that this is equal to b squared. Okay. And it's important that this must be 1. So just make sure that that's a 1. Okay. So if a squared is equal to 9, then to find a, you square root both sides. Okay. B squared is equal to 25. B squared is equal to, right, we're going to square root both sides. B is equal to 5. Okay. Now remember, A is below the X and the B is below the Y. Okay, so let's graph this. Okay. So over here, we said B is equal to 5. So this distance here is going to be 5 and 5. We said X is equal to 3. So this distance here is going to be 3 and 3. And what you do is you just draw a box. So you go up 5, you go down 5, you go right 3, and you go down 3. That's negative. That's positive. That's negative. Okay. So what you'll do is you draw an ellipse. I'll go through those points. And then you're done. And just so you know, for the ellipse and the hyperbola, the video was created by me. So if you forget how to do it when you're working on this tonight, just know that the video will do every example that I do right here. Okay. All right, now, I'm going to give you another problem to do, but I'm going to start it at a different place. Okay? So the problem I'm going to give you is going to look like this. I'm sorry. 4x squared plus 9y squared is equal to 36. Okay? Now, the reason why we know this isn't a circle is because these two numbers are not the same. See, if we have something that looks like this, that's a circle. But the problem here is that these two numbers are not the same. That's how we know that it's an ellipse. Now, the key for this problem here is that we want it to look like this. So this must be 1. So the way you make this thing equal to 1 is you divide every term by 36. So you get x squared over 9 plus y squared over 4 is equal to 1. Okay, so go ahead and work on that problem. So I can start you from here, but if I'm having a bad day, I can start you from here. Okay, so let's erase this. So the first thing you want to do is find A and B. So we're going to start here, and then we're going to go over here. Okay, this is A squared. This right here is B squared. Let's take a look at this. Okay. So we have a squared is equal to 9, so a is going to be equal to 3. We just take the square root of both sides. We have b squared is equal to 4, so b is equal to 2. Okay. So this one is negative 3 and 3. This one here is positive 2 and 2. Oops, sorry. Like that, draw that box. And then I shift it. I said not shift it. And then I draw my little ellipse. And then I'm done. Okay. Now, so this right here is the first variation. There's two variations on this. There's going to be one more. So the first variation is that that's not a 1. So divide everything so that you get a 1. It's a good copy. Okay, so let's look at what happens when we move the center. Okay, so I'm going to give you another formula. So this formula has the center at the origin. Okay. This new formula has center at H and K. Okay. The idea here is that this is going to look exactly the same. This distance here is A, and this distance here is B. But, so this distance here is, oh, sorry, I did that wrong. This distance here is B. This distance here is A. The only difference is, oh, I did it wrong again. That's A and that's B. And the center right here is going to be H comma K. So my center no longer is at the origin. I'm finding first the center, and then I'm moving this much, the same amount left and right, and the same amount up and down to draw my little box that my ellipse fits in. So on the XYZ, you won't necessarily draw the box. You'll just draw the points on the, they'll probably give you this point and that point.
So is the center always 0 with these circles?
No. So in the problems we've done so far, they've been 0, 0. So if I put a 0 and 0 here, I get this. So now with the next problem, I'm going to shift the center. Okay, I'll show you what that looks like. So let's say I have something that looks like x minus 1 squared over 4 plus x plus 3 squared over 9 is equal to 1. Let's say I have something like that. So this is equal to a squared. This is equal to b squared. This is equal to minus h. And this right here is equal to minus k. So your job is to find what is a equal to, what is b equal to, what is h equal to, and what is k equal to. So a is equal to 4, b is equal to 9, negative h is equal to negative 1, k is equal to 3. So figure out what a is equal to, b is equal to, h is equal to, and k is equal to. Okay. So we have square root of 4 is 2, square root of b is 3, h is going to be 1, and if I divide both of these by negative 1, I'll get negative 3. So my center is, well, let me write up here. The center is at 1 comma negative 3. Okay, so draw a dot on the center. Okay, draw your dot on your center. Okay. 1, negative 3. Okay, that's my center at 1, negative 3. So draw your dot there. Now, my A is equal to 2. So from this center, go 2 to the left and 2 to the right. So I'm going to go 2 to the right, 2 to the left. So that distance here is 2. Now, after you do that, so 2 to the left, 2 to the right, and then on this one, go 3 up and 3 down from the center. So from here, you're going 1, 2, 3, 1, 2, 3. So that's your box. And then draw your ellipse in there. And it'd be more symmetric if I didn't have shaky old man hands. So this go like this. And then we're done. Okay, so let's take another break into 10:25, and then we'll do hyperbolas. So I'm going to leave this up here for you guys to copy. If you have questions, just ask questions off of it. But, I'll give you one of these. Does anyone have questions on what's on the board? Okay, so let's knock out the last section. This last section is section 10.4. It's hyperbolas, which is very similar to ellipse. So we're gonna hit all the same beats. Okay. Now, the ellipse and the hyperbola are very similar in terms of formulation. The only difference is that this has a negative. Now, because that's a negative, and you'll see why we drew this box. The way you draw a hyperbola is that we draw an X that goes through your diagonal, through a corner, through the center, and through the other corner, right? We draw a guiding line that looks like that, and one that looks like this. These are called asymptotes. Now, what an asymptote is that it gives us a guiding line. So we're going to start from the edge of this box, and we're going to draw something that looks like a hyperbola that follows the asymptote. It doesn't cross it, but it follows. Like that. Okay. So what a hyperbola looks like, it looks like two parabolas. So go ahead and copy that, and then I want to give you another formula. Now, because this is a negative and one of these is positive, it's also positive to have a hyperbola where the x is negative and the y is positive. So it'd be written like this. Okay. Now I want you to see that the A goes with the X, the B goes with the Y. So the A isn't the first number, it's the number that's below the X. The B is below the Y. So if the Y comes first, the B is still below the Y. Okay. Now the A and B will still be the same. The A is still, how far do I go? Oh, shoot. Gosh darn it. This is A and this is B. The A and B are still the same. This right here is the A. This right here is the B. And then when we draw this, we're still going to draw the same asymptote that goes through the corners of the box in the center. But because the Y comes first, right, the Y is positive, this will go up and down. Right? It's the positive Y that makes it an up and down hyperbola. Now, I'm going to give everyone a second to copy that. So let's try it. Let's do one of these and let's do one of these. And then we'll play around with moving the center. Okay. So we have x squared over 9 minus y squared over, let's say 16 is equal to 1. Okay. So go ahead and find the A and go ahead and find the B. So remember that the A is connected to the X. And then the B is connected to the Y. So draw the same box you did with the ellipse. So the square root of A is 3. Square root of B is 4. So we're going to draw the same box. Now, draw your asymptote. Have it go directly through, corner to corner through the center. Okay. Now, since the X is positive, we start from this end right here, and then we go toward the asymptotes, but we never cross it. They just kind of give us guidance.
Professor?
Go ahead.
When I because I've taken like higher math and I'm doing this review. So when we've done asymptotes, I don't remember ever drawing like an X.
Oh, okay. So usually when you're taking higher math, a lot of times what's happening is you're looking at vertical horizontal asymptotes.
Yeah.
Or vertical asymptotes like this, right?
Yeah.
And really, asymptotes can be any direction.
Okay.
So when you start taking, did you take pre-calculus yet or no?
Yeah, I did. This is like I'm doing for review because I'm old.
Sure. So sometimes in pre-calculus, I didn't actually learn this when I was doing pre-calculus, but the younger people now, when they're taking pre-calculus, they'll actually have diagonal high asymptotes like that. But then they didn't teach that when I was going to school either. So I'm with you. I didn't learn this until I became a teacher.
I was just confused. Okay. Thank you.
So they don't have your horizontal and vertical. They actually could be in any direction. But this was not some, I agree with you. This is new.
Okay, I wanted to make sure.
Yeah. So it's not that you didn't remember. At some point, someone said, we should add that.
Okay. Thank you.
Yeah. So yeah, I do remember I taught pre-calculus in one of my first semesters, and I remember having to go through the book and going like, this is new. There's a lot of stuff here I didn't learn. And you know what the sad thing is? So what happens is with George W. Bush, with really good intention, wanted to be an education president. And I think was really well intentioned about it. And what he said was, what we really should do is we should reward states for doing better, or reward schools for doing better than other schools that share the same demographic. So if you do better than other schools, then what we'll do is we'll give you more money. So you make your test, and if you improve on your test, we'll give you more money. So what happened in California and every state is that every year they made the test easier. They changed the curriculum to dumb it down. Dumb it down, dumb it down, dumb it down, dumb it down. So if you're looking at the 8 years of George W. Bush plus 2 years of Obama, we dumbed down the curriculum for like a decade. So what you were learning at the end of the decade was much easier than what you're looking at the top of the decade, because it was a way for schools to scam the system. It's hard to teach better. It's easy to make the test easier. But you can only make the test easier if we agree that the curriculum is easier. So every year we dumb down the book and we dumb down the test. So that way the schools will make more money. Now, again, I think George W. Bush was sincere about fixing this problem. And he said, this is stupid. Then why don't we just have a national test and a national curriculum? You teach that any way you want, but the test is our test. And it's no longer going to be Scantron. It's now going to be off of an iPad. So we can ask you a lot harder things because, students figured out, oh, I just plug in the answer, and the answer that works when I plug it in, that works. And the teacher's like, yeah, I don't have to teach you math. I can just teach you to plug in. So then, again, I think out of real sincerity to make real change, and then like PP's attacked all the time about No Child Behind. It was the schools that were deliberately looking for loopholes at the cost of student education. What he was trying to do was reasonable. Now, the mistake that he made was that he said, on this day, everyone teaches this much, whether your students get it or not, and then on the next day, you teach this much. So with No Child Left Behind, he goes, that was a mistake. I should not tell you what happens in the classroom. I should just tell you how high you have to jump. And then all these teachers got pissed off because guess what? You had dumbed down the curriculum for 10 years. So all this stuff, they're just throwing out, you don't need to teach this, you don't need to teach this, you don't need to teach this. And these teachers came in and they just became dumber and dumber. They couldn't do the same stuff. So now when Common Core came in, all these teachers left because they go like, I didn't learn this. And then they had this issue where engineers were looking at this and going, I didn't learn this. This isn't important. The Common Core was actually originally created in the United States, but we did not use it. Singapore then used it, and then their students do much better than us. And we figured out like, oh, so Singapore students go to school same amount of hours as us. Singapore teachers make the same amount of money as us. What we should do is do what Singapore does. So if you were a third grader in Singapore, you were learning things that engineers did not learn in college over here in terms of math, just how to approach a problem. So rather than going, maybe I should be embarrassed by what we're teaching in college, we didn't do that. We went, well, I didn't need to learn it, so no one needs to learn it. So the Common Core now, when even me as a math professor, when I go through my kids' Common Core, it's way different from what we learned. Just so you know, that Common Core is pushing your kids. They're going to be better than you. It's great. I love it. When I look at their stuff, the standards are way higher than when I went to elementary school. And oh my God, they're way higher than what they were before. So there's always this content. So with any kind of like public service, I mean, you're seeing it now in terms of like the data, in terms of murders and all that going down. People in government figure out how to juke the stats to make more money. And then at some point, it becomes so ridiculous and we have to reset the standards. So what's going on in the math classes is they're paying us more money if you pass a 200 level math class in the first semester. The government's just giving you money, like, here, take it. So these schools are just creating joke classes where like everyone passes. Just show up and you pass because we'll get money from the government. So there are schools, even one school in our district, which is doing it, where they're just like, yeah, don't worry about hard things, because if we teach you hard things and you flunk, we can't collect that extra little bonus money for passing you. So At Valley College, we're not doing that. But if you go like, why is the curriculum changing? Because the government is always in battle with schools and administrators, which are always looking for loopholes to dumb down the content for more money. Okay, so now that we've done this one, and I get off my soapbox, let's do one like this one. Okay, so what we want to do is, I'm going to start you in a different place. Let's go, let's go 100 minus, oh, I'm sorry, I got it wrong. Let's go y squared over 4y squared minus 25x squared is equal to 100. So the reason why this is hyperbola is because that's a negative. But the key thing is that this one must be 1. Okay, it must be 1. So the way we make it 1 is what we did last time. Is we divide everything by 100. Now you have to be careful. B squared is what is below the y. A squared is what's below the x. So be really careful, okay? The A always follows the x, and the left and right is always the A. The up and down is the B, and it always follows the y. So go ahead and find B and A, and then draw your little box. Excuse me. So we have B is equal to 5 and A is equal to 2. So draw your box. Going through here, here. And going through here and here. Now, draw your asymptotes. Okay, give me a second. Sorry about that. My son's making an omelet. He's bagging pots. So. So we're gonna, well, it's not a very good rectangle, but we'll just fake it. pretend that it is. Okay, now, that did not go through the center, did it? Okay, so in theory, let's pretend that this is a good box. I've got to go through the corner and then through the center. Okay, now, because the y came first, this goes in this direction, up and down. Okay, it's this one here. It's not because we started with this 4 over here. It's because we ended up with this positive y squared. Okay, now we can move the center by adding h and k in the same way. Oops. By adding h and k in the same way we did the ellipse. And then same thing here. Now, the important thing to remember is just like B, K stays with the Y. Okay? So if the Y is second, the K is in that second term. If the Y is in the first term, the K and the B are in the first term. So the K and B follow the Y. Okay. So let me give everyone a second to breathe and copy. Okay, so let's try doing one of these up here. So let me erase this. So we'll do one of these, and I'll explain why this is important and why this is why the hyperbolas have fulfilled these type of shapes have fulfilled this quest that mankind has had since the beginning of time. Okay, so I'll explain that in a second. You didn't think you were doing something that important, but you are. But you are on this one. Okay. Now let's work on something like this. Okay. So know that this right here is minus h. This right here is a squared. This right here is b squared. And this right here is minus k. So what you want to do is find out what h, k, a, and b are. So we have minus h is equal to minus 2, so h is equal to 2. Minus k is equal to 1, so k is equal to negative 1. A squared is equal to 9, so a is equal to 3. B squared is equal to 4, so b is equal to 2. So my center is 2 comma negative 1. So go ahead and draw a dot on 2, negative 1. Okay, so 2, negative 1. Now from this point, go left 3 and then go right 3. And then go up 2. draw your asymptotes that go through the corners. And make sure that when you draw your hyperbola, that's going in the right direction. Look for which variable is positive and open your your hyperbola in that direction. So go ahead and copy that. Let's do one more.
Professor,
Go ahead.
because we have the add on the equation, wouldn't that be the...
Oh, you're right. You're right. This should be a subtraction. Thank you. Thank you, thank you. So let's do this one more time. We're going to do this one next, right? So the y is going to come first. So be careful where you pick up your A and your B and your H and your K. Okay. So try doing this one.
Professor?
Go ahead.
I have a question. So,
Sure.
in the bottom, the example where you said y minus k squared divided by, is it the b squared in the bottom, or b squared a squared, or is just b and a?
Oh, I see. Yeah, it should be b squared a squared. Yeah.
Okay.
Yeah.
Thank you.
Thank you. Okay, so for this one, go and find your A, B, and your H and K. And I'm not going to tell you which one it is. I want you just to be careful. Because if you make a mistake, you'll make a better example. Now, remember, the B is underneath the Y. And then the K is next to the Y. So go ahead, find your H, K, B, and A, and then, actually, let me change to A, B. And then draw your box. Okay, now remember, because the Y is coming first, this will be up and down. So I have H is equal to -3, K is equal to 2, A is equal to 1, and B is equal to 2. Okay, so be sure to put a dot on the center, -3, 2. That's my center. Okay. Now I'm going to go left and right 1. And then I'm going to go up and down 2. So up to here, down to there. Not very pretty. Okay, so go ahead and copy that. Then I'm going to tell you why this is one of the most important things that we've done in mankind. Okay, I'm going to leave this up here for you to copy. And let me just kind of tell you a story. We started this class with the story of how we came to use Roman numerals, but Arabic Hindu numbers. So we're going to end with one of the classic stories of math. Okay. Now, understand that about 1,000 years before Christ, this is in ancient Greece. There is no Catholics. There is no Christianity. Didn't even exist at this time. Now, what happened was you had this explosion of learning in Greece. Now, what happened was we had these three great philosophers. We had Socrates, we had Plato, who then created the first university, and then we had Aristotle. Okay, Aristotle thought he was going to take over Plato's university, and he didn't. And because he was so pissed off, he wanted the world looking at Egypt, just going through the entire empire, looking at how science worked in other countries. And he came up with sort of our first model of science. And Aristotle came up with a lot of different ideas, or he would promote certain ideas. And because it was Aristotle, for 2,000 years, it was like the Bible. Aristotle said it, it must be true. So Aristotle is sort of the father of science. So all of our thinking within the Western civilization, it narrows back to Aristotle. If this was Asia, most of their thinking goes to Confucius. They have a different tree than us. So Aristotle did not come up with this idea, but he promoted this idea that the sun was in the middle of the world, middle of the universe. I'm sorry, the earth was in the middle of the universe, and then the sun went around the earth, so did the moon, and so did the stars. And that we had a Earth-centric universe. And it was very good. It made a lot of really good predictions. And for 2,000 years, that's what we believed. Now, what happened was during the Enlightenment, after the Dark Ages, so Rome came up, they adopted all of the Greek ideas, and then all of a sudden, Rome was destroyed by the Germans, by the people from England, by people from the Mongols. They just got wiped out because at a certain point, they just became this corrupt empire and they got wiped out. Now you had no police force to sort of maintain security, and you had what we call the Dark Ages, where people would just be loyal to whatever king or baron happened to be around them that would give them protection. And when you are starving and worried about dying, science isn't happening. And at this point, algebra is burdening in the Muslim world, the Arab world, where they are having their enlightenment moment, where they are bringing scientists from all over the world, and they came up with algebra and the beginnings of chemistry, which was alchemy. Now, Western Europe then starts to develop. You start having countries that could protect themselves. So then we had what's called the Enlightenment. Now, as these countries, Italy, Portugal, Spain, England, are conquering other territories, they're trying to convert people to Catholicism or Christianity. At that time, it was mostly Catholicism. Now, there's a problem with Catholicism. See, this model of the universe is wrong. The way we see it now is that we have a sun in the middle, the planets go around this, and then we're revolving in a galaxy. Now, galaxies were not discovered until just a few decades ago. So even the concept of galaxies, very new. But we had this model that was good for a lot of things, but not everything. So they went to Copernicus, who was a priest. And they go, hey, Copernicus, you like this whole astronomy thing. See, the thing that happens is that when we conquer native people and we say we have the superior religion, you should be Catholic, they don't believe us because we can't tell them when to plant the crops. Whenever we try to predict the summer solstice and the winter solstice, our predictions are worse than the people that we're conquering. So if we can't tell people the most important days that they need. When do I plant and when do I harvest? Why would our God be better? So could you look at this and fix it for us? And then Copernicus goes, yeah, sure, I'll look at it. Let me take a look at it. I like this science thing. Now, where Copernicus went to figure out how the universe works was not a telescope. He went to the Bible. He went to the Bible and read the Bible and says, well, it says God is the light. And it really makes sense that if I was to take a biblical understanding of the universe, shouldn't God be in the middle? Especially since all over the Bible, they keep calling himself the light. I'm the light, I'm the light, I'm the light of the world. God must be the sun. And the earth must go around the sun. And then the planets go around the sun. And then when he did the calculations, it worked better for some things, but not all things. See, Copernicus thought God's in the middle. And what is the most holy shape? Circle. Circle must be the holy shape because it's symmetric, it's perfect. God, creation is perfect. So it only makes sense that the trajectories that we move are in the universe are perfect. So he said we go around in perfect circles. So it fixed some predictions that this one missed, but this one still made predictions that this one missed. It had been around longer. People had sort of learned how to fudge the numbers a little bit. Now, Copernicus, again, this was created by a Greek, a pagan. Christianity did not even exist at the time that this was created. But the way education worked was all borrowed from the Pythagoreans to the Plato University, which became the Catholic seminaries. So not only did they take the structure of the content from the ancient Greeks, they also the structure of how these schools work, they also took, well, the non-religious science of the time. So at the time, the Vatican says, if you don't believe in this, you don't believe in God. So believing in this Earth-centered universe was part of you being Catholic. So Copernicus figured out that this is better, it makes better predictions. But he was scared to tell anyone. So he wrote a book about it, but he didn't tell anyone. And then on his deathbed, he whispered, just so you know, the sun is the center of the universe. I wrote a book about it. It's in my drawer. And then he died. So he told someone on his deathbed they wrote this book. So the guy took the book and he's like, oh my God, if I show this to people, the Catholic Church is going to kill me. So he went to some publisher and they go like, I want to honor him because he said this is good science, but I don't want to die for it. So the publisher figured out what we'll do is on the very first page, we'll say everything in this book is wrong. So they published the book, and on the first book, it says, this is just for entertainment, nothing is true. Can you imagine opening your math book and the first page says everything in here is wrong, this is just for fun? Now, you had a guy named Bruno. Bruno looked at this, and he was like a noble. He looked at this and goes, this makes sense. I like this. And he started promoting it. Now, Bruno had two problems. One, he's promoting a system that was not supported by the Catholic Church. And the other thing is that he didn't believe in the Trinity. So then they set him on fire. A lot of people who are atheists like to go, Bruno, he's our guy. He died for this system. But really, it was because he didn't believe in the Trinity. And the fact that he also didn't believe in this, that didn't help either. So if you're an atheist, where do you go to pray? Right? Where do you go to meet? Where is your altar for the atheist? So what happened was in Rome, a couple hundred years ago, they every so often, the Catholic Church, they codify the rules. So for example, the current Pope has said, people have asked him, so do Muslims go to heaven? He goes, who am I to say who goes to heaven? And then people go, oh, are you saying Muslims go to heaven? I'm like, I'm not saying that. I'm just saying, who am I to judge? Now, what happens is as technology, as different things happen, as popes say things, at some point you need to like say, okay, we've said a lot of stuff. Let's all meet and just say let's plant a flag here. So they had one of the moments in Rome about 200 years ago, and what happened was the Freemasons, who were very pro-science, they wanted to protest it, so they built the statue of Bruno. Let me show you where it looks like. Let's see. Is this it? No, that's not it. Maybe this one's it. That's the statue of Bruno. It's in the middle of a little market. People really disrespect it. They like lean their chairs against it and stuff like that. But when I went to Rome, I made a pilgrimage to go see the Bruno statue. I love the story. The Bruno statue faces toward the Vatican, and on it you see all these love letters from atheists that goes, because of you, I don't believe in God, and because of you, I pursued science. So there's all these love letters to Bruno. He is sort of the altar to the atheists, right? And then the Vatican is always trying to tear it down, and somehow the Freemasons have the power to like just keep it there. So the people around it are not very respectful to it, but it is like a pilgrimage site to like very, very like vehemently pro-science people. Okay, now, next came Galileo. So Bruno was just some nut, okay? And he wasn't one of everyone, so him saying this stuff was not very helpful. But you're not really Catholic. You seem to be like saying stuff that is attacking Catholicism, so we'll just get you out of the way. Then came Galileo. Now, Galileo was a superstar. I love Galileo. Now, for those of you who think being right is all that matters, just so you know, it's not at all. When my professor tried a tenure, he's one of the 5 best people in the world. They didn't tenure him. They didn't want to compete with him at my university. So for someone like that to not get tenured made me realize when I got this job, you know what? Most important thing for tenure is people like you. Now, Galileo was one of those people who went through everything Aristotle said, right? This is 1600s. So for 2,500 years, everyone just believed what Aristotle did. And Galileo went down the line and said, yeah, you know what? This is wrong. And then he would do an experiment, prove it. This is wrong. He would do an experiment and he would prove it. And you just go down the line. And imagine if you spent your entire life memorizing everything that he said, and Galileo was disproving it, then guess what? Your education was worthless. So they kicked him out of the university. Now he's still a star. And then he takes on this case and he goes, this is not true. I can prove it. And he proves it in a lot of ways. Like the original concept was that the sun is a perfectly round shape and it's perfectly smooth. And Galileo got a telescope and aimed it at the sun. And he showed that there were like sunspots and it wasn't perfectly smooth. So he could just give someone a telescope and disprove it. Now, Galileo was a schmoozer. He's like Jon Stewart. When he not only does he tell you you're wrong, he says it with charisma and style. He makes you feel like this big because he's right, and the way he writes about it has so much style. So he and the Pope are really getting along. So there's this new Pope. The Pope is not very serious about Catholicism, and he likes hanging out with Galileo. And Galileo thought, good, I've got the political backing. I'm going to write a book explaining how this is right and this is wrong. So Galileo writes his book, and then when the Pope reads it, he goes, there's 3 guys. There's a guy asking a question who's neutral. There's a smart guy, and there's a dumb guy. Why is it that the dumb guy always quotes my questions? So the Pope looked at his book and goes, you're mocking me. So he put him under house arrest, and that's where Galileo died, in his house. He continued to do really amazing experiments from his imprisoned in his villa, but he was sidelined. Okay. Now, while this is happening, another 100 years pass, and there's this guy named Kepler. Kepler goes, all right, I'm very Christian. I really am devout. And I'm just going to show people that Galileo was correct, and you can believe in a sun-centered Earth and in God. I will prove it mathematically that's true. So he went and he tracked all the planets, and he found out that Galileo was wrong, that this almost worked but doesn't quite work. What he didn't get is that the orbits were ellipses. They look like this. They were not circles. Now, this sent Kepler into this emotional depression, because how could God have an ellipse? So then he went and studied ellipses and found that ellipses were beautiful. In math, there were much more, there's much more you could do with ellipses than you can with a circle. And then he said, of course, man thinks in circles, God thinks in ellipses. Ellipses. Now, what happened after that is that then they're wondering why the ellipses. So there's this guy, Halley, from Halley's Comet. He's with this guy, Hooke, who discovered how springs work, and this other famous mathematician, and they're trying to figure out, how does this work? Why is it an ellipse? And then they went to, then they had a bet who could figure out. Hooke said, I know what it is, but I'm not going to tell you. And everyone thought, no, Hooke's a jerk. Hooke always says he knows everything, but he doesn't know. So Halley went to go talk to this young rising star scientist, and he went to Isaac Newton and goes, we have this bet, and I can't figure it out. And Newton goes, oh, I know. You just, gravity, mass, and then there's some constants. The mass of the two objects divided by r squared. It's because you divide by r squared. That's why you get an ellipse. And he goes, how the hell did you do that? He goes, I don't know. I figured it out a long time ago. He goes, you just discovered the first question man asked. When you came out of the cave, you looked at the sky, the things moved around in these patterns, and you just you answered it, and you didn't keep the proof. He goes, I'll do it again. So Hooke convinced Newton to write the Principia. So Newton discovered calculus, created it, and then redid all his proofs in geometry, because calculus didn't exist. So if you come up with formulas that you go, this is from this math that you don't understand, no one's going to believe it. So he discovered calculus, he came up with all the formulas in physics, and then he rewrote it in geometry. He wrote it in a very difficult way because he didn't want to be bothered by the peasants. Listen, if you can't read it because it's hard, then don't bother talking to me. I don't want to explain it to you. So Newton then, so then Halley goes, okay, great, we're going to publish this now. So he went to the Academy of Sciences and said, hey, we got to science this. We got to publish this as the most important book ever written, other than Darwin's book. And they go, you know what? We made an encyclopedia of the fishes, and we ran out of money because turns out nobody wants to buy an encyclopedia of the fishes about fish. So then Halley went, okay, I'm going to mortgage my house, and I'm going to print this book because this book is so important. If Newton was wrong, Halley would have lost his house. But Newton was right. And it became the two most important books ever written in terms of science is Charles Darwin's, right, Origin of Species, and the Principia from Newton, which answers all the questions of how the stars move. When I throw something, where does it land? And the reason why I like conic sections is that every shape of a conic section is how an object interacts with gravity. So if I have a sun here, if I have no sun, I have a point. If I have no sun in motion, I have a line. If I have a sun and an asteroid and it gets bent by the sun, but doesn't get captured by it, I have a parabola. If I go by the sun and captured by the gravity, I have an ellipse. And if I throw it in absolutely perfect at the right distance and the right speed, I have a circle. So all the shapes from the conic sections are what we see in the sky. Now, for each one of these, right, is every iteration of x's and y's. So this will look like x is equal to, this is equal to x plus y is equal to 3. This is equal to x squared is plus y is equal to 3. This is equal to x squared plus y squared is equal to 3 divided by 4 divided by 4. If we go through every iteration of x's and squares, what we get is every shape of the conic sections. So this then also pairs with, hey, if I have squares and x's, what are all my shapes that I see? They're all the shapes that you see in the trajectory of the sky. Anyways, tomorrow we'll start review. I'll hang out afterwards. But I really appreciated, having you guys in my class. Even though I haven't gotten to see you guys, if you guys need help in terms of letters of recommendation or essay writing for a transfer, just talk to me. I have a lot of samples and examples for you. Okay? All right. Thanks, everyone. And I'll hang out if you have any questions.
Professor?
Uh-huh.
I did have a question on my practice test 3. There was a problem with the graph that asked if it was a one-to-one function.
Uh-huh.
And I thought it wasn't, but I got it wrong, and I don't know why.
Okay, let me look at my mail right now. Let's take a look. Did you email it to me?
I can't access it anymore because it says time has run out.
Oh, okay. Was it on the midterm or was it on quiz 3?
Practice quiz 3.
Practice quiz 3. Okay. So let me pop it up really quick. I'll change the date so you can access it later today.
Okay, thank you.
1 second. So let's go practice quiz 3. The one-to-one question. Was it a graph or was it a list of points?
It was a graph.
It's a graph. Oh, okay. Oh, I see. It looks kind of like this, right?
Yeah, exactly.
Yeah, I can see where it is. The idea here was that this was an asymptote. So it's slowly going up, but not quite hitting it. So the idea here was that since it was never actually flat, that's why it's one-to-one.
Oh, okay. Yeah, that's what threw me off because I thought it was on the x-axis. So
yeah, it's a little tricky. Yeah, it meant for the axis to be a asymptote. So in theory, it's slowly going up toward it.
So should we assume that for all graphs that look like that?
Yeah, pretty much. Yeah.
Okay.
And then not just for this class, but every class after this.
Okay. Thank you.
Yeah.
And the practice will be available later on in the
Yeah,
day.
I'll change it right now, right after class. That one's easy for me to change.
Appreciate it.
Okay, no problem. Anyone else have a question? Okay, thanks everyone, and good luck on quiz 3.
Thank you, Professor. Have a nice day.